In this video, I'm going to show you how to conduct a hypothesis test for Pearson's correlation. In the previous video, you learned how to conduct Pearson's correlation in Excel. However, the correlation coefficient we found could only be applied to this data set. So the positive, strong relationship we found between sales calls and copiers sold can only be used to describe this data set. Oftentimes, we're interested in if we can generalize our findings. So for example, if this is a sample of employees, the corporation may be interested in if this positive relationship is occurring among all of their employees. So can the findings from the sample be generalized to the population? And hypothesis testing will answer that question for us. The steps of hypothesis testing are the same as the steps that you learned in the previous module. The first step is to select the test. If you look on ISMS, you will find a handout, and this handout will walk you through all of the different steps. I'm going to use this handout as a guide throughout the video. So first we are going to select the test, and the name of the test is Pearson's correlation, and we are going to conduct a t-test for the correlation coefficient. So again, the purpose of a Pearson's correlation is to determine if there's a relationship between two quantitative variables. The hypothesis test takes sample data, and then it draws a conclusion about the population. So is the relationship in the sample strong enough to suggest that there's a relationship in the population? So if you look at the problem description, you can see that an analyst wants to determine if there's a relationship between the number of sales calls and the number of copiers sold. They take a sample of 10 employees and they collect their sales data. So we have data from just 10 employees, and we're going to take that data and we're going to conduct a hypothesis test, and then we're going to draw a conclusion about the entire corporation. So all of the employees, and there's many more than just 10. The second step is to identify the case, whether it's one-tailed right, one-tailed left, or two-tailed. And correlation is easy in the sense that it will always be a two-tailed test in this class. The reason why it's two-tailed is because we're hypothesizing that there could be a positive or negative relationship. We're just looking for a relationship. If we were to specify that we're looking for a positive relationship or a negative relationship, then we would conduct a one-tailed left or a one-tailed right. However, the examples that will be covered in this class are always going to be two-tailed. The next step is to state the hypothesis. The null hypothesis is that there is no relationship between the two variables. If there is no relationship between the two variables, that means the correlation coefficient is going to be 0. So our null hypothesis is that the correlation in the population is 0. And this symbol, it looks like a P, it's rho, and it stands for the correlation coefficient in the population. So our hypothesis is the correlation in the population is 0, or rho equals 0. The alternative is the correlation in the population is not 0. Rho does not equal 0. So we can indicate the null hypothesis, and that's that there's no correlation, or that it's 0. And the alternative is that there is a relationship, so the correlation is different from 0. It's not 0. The next step is to determine alpha. And just like in the previous module, this is going to be found in the problem description. It's either going to be 1% or 5%. So again, if you look at the problem description, you can see that we're supposed to conduct a statistical test with an alpha of 0.05. So our alpha is 5%. The next thing we're going to do is we're going to compute the descriptive statistics, and we need these for our test statistic. So we're going to compute R, and we're going to use that using the function, the correlation function. Then we're going to determine N, our sample size, or the number of observations. We're going to use the count function for that. And then we're going to compute the degrees of freedom. For this test, the formula for degrees of freedom is N minus 2. So we're going to determine the correlation coefficient. So we're going to use our CORREL function, and then we are going to select our data. And we got the same coefficient that we did in the previous tab, and that's because we're working with the same data set. Now we're going to figure out the sample size. So we're going to use the count function, And for that, you just take the count of one of the variables and not both of them. And that's just because we want to figure out the number of observations. And remember, each is a pair of observations. So we're basically determining the number of employees in the data set, and it's 10. Then the degrees of freedom is the sample size minus 2. Next, we can compute our test statistic. This is the formula for the test statistic. We're going to take our Pearson's R times the square root of the degrees of freedom, and we're going to divide it by the square root of 1 minus R squared. So we're going to do R times the square root of our degrees of freedom, and we're going to divide that by the square root of 1 minus R squared. And I got 2.93, and I'm going to show 2 decimals. Next, we're going to compute the critical values and the p-value. So for the lower critical value, we're going to do -1 times the t.inv.2t function. And then for the upper critical value, it'll just be the t.inv.2t function. All right, so the lower critical value is -1 times t.inv.2t, because we're conducting a two-tailed test. You can see that it asks for the probability. This is alpha. And then you can see here, it's asking for the degrees of freedom, which we computed over here. And I got -0.230. And then for the upper critical value, we're just going to do t.inv.2t, and we're going to indicate our probability, which is alpha, and then our degrees of freedom. And I'm going to format those both to show 2 decimals. Next is the p-value. We're going to use the t.dist.2t function. We're going to take the absolute value of our test statistic and then our degrees of freedom. So again, x is the test statistic, and we have to take the absolute value of our test statistic and then the degrees of freedom. I'm going to format this as a percentage, and I'm going to show 2 decimals. The next step is to evaluate the null hypothesis, so to determine if we're going to reject or fail to reject the null hypothesis. As in the previous module, there are 2 approaches, the critical value approach and the p-value approach. So we'll start with the critical value approach. So it depends if our test statistic is negative or positive, and ours was positive. So if our test statistic is greater than the upper critical value, we're going to reject. If it's not, if it's less than, then we'll fail to reject. All right, so our test statistic, I'm going to write this down here. Our test statistic, which is 2.93, that is greater than our upper critical value, 2.31. So again, since we have a positive test statistic, we're going to compare it to the upper critical value, and our test statistic is greater than the upper critical value, so we are going to reject the null. We can also use the p-value approach, and for that, we compare the p-value to alpha. If our p-value is less than alpha, we reject. If our p-value is greater than alpha, then we fail to reject. So you can see that our p-value is 1.89%, and that is less than our alpha of 5%. So we are going to reject the null. Remember, the critical value approach and the p-value approach are always going to be in agreement. So sometimes it's helpful to do both, just because it's a way to check to see if you're making a mistake. Because if they're not in agreement, then somewhere along the way you made a mistake. All right, we are going to reject the null hypothesis. If you return to your handout, you can see that the last step is to write a conclusion. If we had failed, we would just say that there's not a significant relationship between the two variables. But in our case, we rejected the null. So we're going to write the conclusion that there is a significant, and we're going to need to determine if it's a positive or negative relationship between sales calls and copier sales. And then we're going to need to elaborate on what we mean by a positive or negative relationship. So is increases in sales calls, is that associated with increases or decreases in copier sales? And again, we can determine if it's a positive or negative relationship by looking at the sign of the coefficient. All right, so let's write our conclusion. So there is a significant relationship, and we can see from our correlation coefficient that we have a positive relationship, and that is because the coefficient is positive. So we covered that in the previous video, so we know that we have a positive relationship. So there is a significant positive relationship between the number of sales calls and copiers sold. Increases in sales calls is associated with increases in the number of copiers sold. Now we know that it's increases with increases because we have a positive relationship. Remember, a positive relationship is when the two variables are changing in the same direction. So we know increases with sales calls is associated with increases in the number of copiers sold.